I now call to order the lecture portion of the Society's 2536th meeting and the 95th Joseph Henry Lecture in what is now the 155th year since the Society was founded on March 13th, 1871. Good evening, everyone. Yes, my name is Larry Milstein, as many of you know, and I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. So welcome to our members, guests, and friends to the lecture portion of today's meeting and tonight's annual Joseph Henry Lecture by Michael Garrett and Adam Thompson on Agentic AI and the Search for Extraterrestrial Life, the SETI-NVIDIA collaboration at the Allen Radio Telescope Array. First, let's thank our sponsors. Number one, the Society is grateful to PSW full-year sponsors, Mike Hilton and Hilton Associates. Thank you, Mike. And to full-year sponsor, PSW member Joe Shulman and the Shulman Family Foundation. Thank you. And the sponsor of tonight's lecture, who asked not to be named, and also asked that we provide this lecture in honor of Dick Garwin as well as Joseph Henry. So let's thank him too. You too can support the Society if you wish. It's easy to make donations online using the donations button in the pull-down menu under members on the top ribbon. Tonight's lecture is the 95th annual Joseph Henry Lecture honoring PSW's founder, first and, well, previously longest-serving president, Joseph Henry. He was the president of the Society from its founding in 1871 until his untimely death in 1878. He was the preeminent American physicist of his time, probably the best-known American scientist then. He's best known for work on electricity and magnetism, paralleling Faraday's contemporaneous work in the UK. His work led directly to the development of much stronger electromagnets and to the invention of the telegraph and the telephone. He actually worked with Morse on the telegraph. He worked tirelessly to spread knowledge of science and was involved in founding and serving in many other science institutions of the time, which at that time was how the knowledge of science was spread. Among other roles, he was the founding secretary of the Smithsonian Institution. And when he died unexpectedly, the Capitol actually closed entirely to mourn his passing, and it was international news. We honor Henry today with this annual series of lectures and by using the Society's ceremonial gavel, carved from the timbers of the White House. Actually, from its rebuilding following the War of 1812, when our good friends, the British, burned down the White House, among other things. No offense intended. The White House, for those of you who are interested in these things, during the Truman administration was completely gutted. Completely. Nothing was left but the shell. And the wooden framing was replaced with concrete, and bunkers were put in and all kinds of other things. And that's how the lumber came to be available for making of things like this ceremonial gavel. Tonight's lecture, as I mentioned, is additionally in honor of another great American physicist, Dick Garwin, who passed away almost exactly a year ago at the age of 97. He was an active member of PSW and logged onto the live streams regularly. While he is most often noted as the person who designed the first H-bomb, he made many, many seminal contributions to science and technology that overshadowed that. including important and often groundbreaking work on parity violation and weak interactions, magnetic resonance studies that are the basis for MRI, work on fast Fourier transforms and digital signal processing in wide use today, the development of reconnaissance satellites and imaging intelligence, laser printing and touchscreen technology, gravitational wave detection, and considerable work on arms control and nuclear test ban verification technologies. His advice was sought officially by every American president from Truman to Trump. Both terms, actually. If you want to know something more about Dick, there's a biography. True Genius, the life and work of Richard Garwin, the most influential scientist you've never heard of, by Joel N. Shurkin. About 10 years ago, before he died, obviously, I asked Dick if he liked the book. 75 years into his career, he said, it was incomplete. It was fun to have him online. I am pleased to announce the following new members. I will be brief in talking about them. Eric Lindquist, a scientist with Evonik, who learned a PSW from PSW member Susan Rich. Karen Gagliano, a business executive who learned of PSW from PSW member Patty Zweibel. Jacob Morgenstern, an attorney with Parry Labs, who learned of PSW from a friend. Ethan Prawl, a PhD student in environmental science and policy, also an attorney, who learned about PSW from reading about it online. Maureen Kotz, an attorney and a consultant, who learned of PSW from PSW member George DeVow. I apologize for mispronouncing your names. Seth Morris, a senior data scientist with ICF, a returning member of the Society, having returned to this area from places far afield. Ian Frankel, a federal growth lead at Jackson AI, who learned of PSW from PSW member Frederica Dorema. Eddie Brown, a scientist at the Planetary Science Institute, who learned of PSW from PSW member Kirby Runyon. Sophie Nixon, a student at GW, who learned of PSW through PSW member Connor Nixon. And tonight's speakers, Mike Garrett and Adam Thompson, who I believe learned of PSW from the invitation to speak tonight, and some of whose interests will be clear from tonight's lecture. All members are entitled to a signed copy of Compendium Volume 17 of the Bulletin of the PSW. If you've not received yours, come and see me after the meeting. All members are invited to the pre-lecture receptions and dinners with the speakers for camaraderie and interesting discussion. If you're not a member and you're interested in membership, you can access a membership application on the PSW website by clicking the blue Join button on the homepage, upper right-hand corner. And if you're here in the Powell Auditorium, there are business cards in the back with QR codes that will take you directly to the membership application. PSW Science membership is open to everyone with a genuine interest in science and in the objectives of the society. Recording secretary, oh yes, if you're not a PSW member, please join now. Okay, recording secretary Scott Matthews will now present the minutes of the 2535th meeting and the lecture by Harris Lewin of ASU on the Earth Biogenome Project, Leading the Library of Life.
Thank you, Larry. Good evening. On April 24th, 2026, members of the Society and guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2535th meeting of the Society to order at 8:01 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, announcing new members, and inviting guests to join the Society. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Kelly Fast, titled Finding Asteroids Before They Find Us. The minutes were approved pending a minor correction. President Milstein then introduced the speaker for the evening, Harris Lewin of Arizona State University. His lecture was titled, "The Earth Biogenome Project, Reading the Library of Life." The speaker began by describing the Earth Biogenome Project, or EBP, as a global scientific moonshot with the ambitious objective of sequencing, cataloging, and characterizing the genomes of approximately 1.6 million known eukaryotic species within the next 10 years. He said that this initiative is not merely a cataloging exercise, but a foundational effort to establish the critical genomic infrastructure necessary to support global conservation, advance the bioeconomy, and enhance international biodefense and biosurveillance capabilities. The speaker provided a comprehensive update on the strategic phases and technical progress of the EBP. He reported that the project is currently executing Phase 1, which targets sequencing approximately 10,000 species. This phase aims to produce high-quality reference genomes representing at least half of all known eukaryotic families. Lewin indicated that this milestone was within operational reach. The speaker outlined Phase 2, which will expand sequencing, computational pipelines, and analytical capabilities across international facilities to encompass roughly 150,000 species. Lewin claimed that the project has already sequenced over 5,600 genomes to date, and that more than 4,000 of these sequences meet rigorous reference quality assembly standards, demonstrating the project's commitment to high-fidelity data. Lewin detailed the core technical impacts and broad scientific utility derived from the EBP's outputs. He emphasized that the project's focus on chromosomal-level assemblies provided deep temporal resolution, enabling researchers to reconstruct genomic history, track chromosomal rearrangements, and analyze genome structure across approximately 200 million years of evolutionary history. The speaker discussed the practical applications of this data. For conservation biology, these high-quality reference genomes are vital for precise action, allowing scientists to assess genetic diversity, monitor inbreeding metrics, and understand the adaptive capabilities of threatened species. He said that biodiversity and species conservation are critical to, quote, essential ecosystem services, such as food, medicines, raw materials, clean water, clean air, climate regulation, and recreation. Lewin said that biodiversity underpins the $4 trillion bioeconomy. From a strategic and security perspective, he underscored the fact that comprehensive genomic data significantly enhances international capability to detect, track, and mitigate biological threats, and thereby enhance global biosurveillance. The speaker discussed the way in which advancing technology has exponentially decreased the cost of genomic sequencing while simultaneously increasing the speed of processing. For example, the technique of sequencing by synthesis, which allows clonal amplification of DNA fragments with distinct fluorescent colors, reduced the cost of sequencing by approximately 3 orders of magnitude between 2007 and 2009. The speaker ended his talk by showing how DNA sequencing can be used to map vertebrate phylogeny back approximately 560 million years, tracing the evolution of modern species to their common ancestors. The lecture was followed by a question and answer session. A member on the live stream asked if EBP was concerned only with mapping the base pairs that code for genes, and what was the importance of mapping the non-coding regions. Lewin responded that EBP is mapping the entire genome, not just the genes. He said that a wide variety of techniques would be used for gene sequencing annotations, the process of identifying and attaching biological information to a raw DNA sequence, and thereby mapping the functions and structures associated with a specific sequence. A guest asked if researchers are now rethinking the idea of taxonomy, given the new genomic data produced by EBP, and if so, what are the guiding principles? Lewin responded that genomics is being used to improve taxonomy every day, giving examples of an organism that had recently been reclassified to a completely different genus. He said, quote, species are being reclassified all the time, even mammals, end quote. A member asked why many simpler organisms had large, complicated genomes, while more complicated species had smaller genomes. Was there some form of, quote, gene optimization occurring? Lewin responded that the complexity does not correlate with genome size. The larger size of some genomes is due primarily to repetitive elements or transposons. He said, quote, "We don't know why evolution is just tinkering." He said at some point the repetitive sequences must have provided some evolutionary advantage. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 17 of the PSW Bulletin. He then announced speakers of upcoming lectures and made a number of housekeeping announcements. He adjourned the Society's 2,535th meeting of the Society at 10:02 p.m. Eastern Time. Temperature in Washington, D.C., 18.3 degrees Celsius. Weather, mostly cloudy. Dinner attendance, 35. Lecture attendance, in person, 75. Live stream, 42, for a total of 117 viewers. Views of the video in the first 2 weeks, 309. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Scott. Are there any comments or corrections to the minutes? Hearing none, I will entertain a motion to accept the minutes as read. Have a second? All members in favor of accepting the minutes? All those opposed? The minutes are unanimously accepted as read and will be posted to the website in due course. We now turn to tonight's lectures by Michael Garrett and Adam Thompson. I'm going to give a short introduction to them both right now, and then Mike will get up and give his part of the lectures, and then Adam will give his, after which we will have a question and answer period with both of our speakers on the stage in those wonderful chairs you see there. So, Mike is the inaugural Sir Bernard Lovell Chair of Astrophysics at the University of Manchester and Chair of the SETI Permanent Committee of the IAA, among other appointments. Previously, he was Director of the Jodrell Bank Center for Astrophysics, General and Scientific Director of the National Institute for Radio Astronomy in the Netherlands, and Director of the Joint Institute for Very Long Baseline Interferometry in Europe. Mike developed the technique of wide-field, very long baseline interferometry and spearheaded the rollout of real-time VLBI across the European VLBI network and beyond. He has also been instrumental in finalizing the design concept for the Square Kilometre Array telescope currently under construction. Among other honors and awards, he's an elected fellow of the Royal Society. Mike earned a BS in astronomy at the University of Glasgow and a PhD in radio astronomy at the University of Manchester. Adam Thompson is head of product for edge supercomputing at NVIDIA. His technical focus is edge and high-performance computing for real-time AI signal processing, particularly high-speed sensor in-out connected to GPU-accelerated compute, and the applications of deep learning to RF data. He's best known for helping build GPU-based platforms for real-time scientific and sensor computing, and for creating QSignal, a GPU-accelerated signal processing library written in Python and integrated in QP, and widely used in sensor processing communities. Adam earned a BS in electrical engineering at Clemson and an MS in electrical and computer engineering at Georgia Tech. Mike will speak first, followed immediately by Adam. All questions will be fielded during the question and answer period following the lecture. With that, Mike, the stage is yours.
So, good evening. It's a great pleasure and very much an honor to be here this evening. I will try and not burn anything down while I'm here. So what I'm going to talk about today is the search for extraterrestrial intelligence, SETI, also more recently called technosignatures, so looking for anomalies in astronomical data that might be the telltale signs of intelligence in the universe. I'm also going to talk about why AI is so important for this field. But the real expert on AI is definitely Adam here. So he will focus really on the amazing progress that's been made, especially here, in California, Northern California, the Allen Telescope Array, and trying to integrate AI into the search that we are making for intelligent civilizations elsewhere in the galaxy. So I'm going to give a talk that I know that you've heard previous speakers talk on the topic of SETI. I think this is probably going to be a little bit different. I usually try and come to this topic from maybe a different direction from the direction that most people take. I'm not really a sort of SETI scientist as such. I really see myself as an astronomer that comes to this topic, especially in terms of sort of looking for anomalies in astronomical data, things that, are a little bit different and may have, this potential explanation of being artificial, being generated by technology, not our technology, but someone else's technology. But I want to start just to bring everyone on the same page with what I would call sort of, traditional approach to looking for technosignatures and looking for extraterrestrial intelligence. So on the right-hand side, yeah. On the right-hand side, you'll see the kind of signals that people are looking for example, the Allen Telescope Array. Now, these are pretty peculiar signals because they're very, very powerful. So you're looking for a very, very powerful signal, but the signal is also coherent. So in some way, you kind of condense the signal either in frequency, which is what you see here. So a lot of power, maybe something of, approaching 10 to the 13 watts, so 1,000 billion watts. And you try and force that into just a few frequency channels, so into a few hertz of bandwidth. Now, the reason that we're looking for these kind of signals is because, first of all, that's what we have done in the past when we've tried to communicate with radio waves. We've tried to use narrowband signals and we've modulated them in some way. So we've rapidly changed the frequency, the central point of the frequency of a signal, or we've modulated the power of the signal. So that's one reason that we're looking for these kind of signals, because technology can produce these. And the other reason that we're looking for them is that nature itself, so if we look with a radio telescope at planets or stars or galaxies, they produce very broadband emission. So they don't produce anything that looks sort of like this very narrowband signal that we see here. So that's what we're typically looking for, especially when we think of how we do SETI today. I'm going to argue that in the coming years, we might also be able to do SETI not only in this way, but also in other ways. But before I get there, I also want to introduce this concept that when we're looking for these narrowband signals, there's a velocity difference between us here, with our radio telescopes on this planet, and a transmitter on another planet. The velocity is always changing because, for example, our planet is in rotation. It's also going around the sun, and that may also be true for their planet. So the velocity between the transmitter and the receiver is continually changing. And I'm sure many of you are familiar with these waterfall plots, so that the frequency of the signal, because of this relative motion, and because the relative motion is always changing, then rather than having a signal that's straight up and down in terms of, maintaining the same frequency over time, you actually see that this narrowband signal moves from one channel to another channel. And it does it fairly rapidly because of the rotation of the planets. Typically, one would sort of estimate that you're moving from one channel to another channel every few seconds. So that's actually a little bit of an advantage, that there is this relative motion between the transmitter and the receiver, because we are also producing many of these narrowband signals here on this planet. But the thing is that we are fixed to the Earth, and typically most of the other signals that we're producing for communications, for example, they're also fixed to the Earth. So they really sort of move up and down. They maintain the same frequency. There's no relative motion between the receiver and the transmitter. So you don't get what we call this Doppler drifting. So you get this drift because of the Doppler effect due to the velocity changing between the receiver and the transmitter. So there's a few other things that are kind of hidden in our assumptions about, looking for these narrowband signals. The first is that if you're going to take something like 1,000 billion watts and stick it into a few frequency channels, then that's a very deliberate thing to do. So that's really a beacon. That's a civilization that's decided to say, hey, we're out here. We're producing this very weird narrowband signal for you to be able to detect. So that's one assumption that's in there. And the other thing that we've already talked about is that we're transmitting these coherent signals. And the other thing that's a little bit weird about all of this is that the kind of technology that we have today when we are communicating with radio waves, for example, is rather different. We're using broadband systems typically nowadays, rather than these very narrowband systems. And so if you look at the last 100 years of radio technology development, it looks a little bit like this. Maybe it's easier to understand if you look at it in terms of this figure. We started off with a few very powerful systems, again, very narrowband systems, so using amplitude modulation or frequency modulation to convey information like radio stations and TV stations. So there are a few of these. They were working at low frequencies. They were sort of pretty well isotropic, at least towards the horizon. So they weren't, the gain in these systems was quite low. So you go from that situation to the situation that we see 100 years later, where rather than having a few radio transmitters, we have millions of them. Actually, we have billions of them. Everyone has one of these things in their pocket. It's transmitting, it's receiving, it's communicating with cellular towers. There are millions of these on the planet. We have Wi-Fi systems. This whole room is pervaded by broadband radio signals, and some of it leaks out into space. So our technology has changed, and most of SETI at the moment is really looking for this kind of signal, rather than this signal. And I want to be clear, I'm not saying that that's a mistake, because narrowband signals, because of their characteristics, they're really easy to detect against the background of sort of natural cosmic sources. So we should definitely be doing this. But I think we also have to consider that actually other civilizations will be probably a bit like ourselves, and using all of the electromagnetic spectrum that they can get, and using broadband systems, also not just at low frequencies, but also at higher frequencies, and also with quite a lot of gain. So these systems typically have more gain than the systems that we have over here. They're more directional. Okay, so you could ask a question, are we actually filtering out potential technosignatures? Because we're very much looking for this kind of signal, but there's a good chance that civilizations are not just producing very narrowband signals, but they're producing lots and lots of broadband signals. And this leakage radiation that we produce, for example, here on this planet, I feel that it's actually time that we started thinking about how we can not only detect this, but also detect this broadband emission. And I'll argue that AI is actually one of the tools that we really need to have in place in order to be able to do that. So I want to make a diversion. You've probably encountered the Kardashev scale in possibly other talks. So Nikolai Kardashev was a Russian astrophysicist. He was working in Moscow. He was doing SETI in the early 1960s. And he kind of started to ask some really fundamental questions, things like, what part of the spectrum we should be looking at. He kind of gravitated towards frequencies between 1 and 10 gigahertz for various reasons. But he also started to think about how difficult would it be to actually detect another civilization? Like, how powerful did those civilizations need to be in order for him to be able to detect those with the kind of technology he had back in the day? And so he kind of stumbled upon this idea in the process of thinking about civilizations in terms of the energy that they could harness, the energy that they were actually using. And so he came up with these different, what we call now Kardashev types. So you have a type 1 civilization, for example, as shown here. That's basically a planetary scale technical civilization that's able to use all the energy resources associated with a planet. And that includes the incident sunlight coming from the host star. So that's a lot of energy. It's about 10 to the 17 watts. It's about 3 or 4 orders of magnitude more than we actually currently are able to harness today in our own society. So this is a type 1 civilization. You begin to go into the realms of science fiction when you start talking about type 2 civilizations. So this is a civilization that can basically harness all the energy associated with its host star. So in the case of the sun, that's about 10 to the 26 watts. So that's a lot of energy, often associated with the ideas of a Dyson sphere or Dyson swarm. And then you definitely get into the realms of science fiction when you start thinking about a civilization that basically spans the entire galaxy and is able to harness all the energy associated with all the stars in that galaxy. So people have criticized this scale for decades, in a sense. But actually, especially when you think about AI today, the real bottleneck for AI in many different ways is actually being able to harness energy, being able to have the power supply in order to be able to do the computation that you need to be, or to appear to be, a very, very clever thing. So it's not perfect, but I think it gives us, an interesting and good way to think about other civilizations in comparison to ourselves. So one of the things I've been working on recently is thinking about, we have a rough estimate of what our own sort of leakage radiation is, especially in the radio part of the spectrum. And in Manchester, myself and some of the PhD students there have been working on this. So it's a logarithmic scale, the Kardashev scale. So we are roughly, this type 0.7 civilization. So we are 3 or 4 orders of magnitude away from being a type 1 civilization. But we can make sort of reasonable estimates that the peak in our radio leakage at the moment, around about a few gigahertz, is of order 100 watts per hertz. So if you were on another star and you look back on the Earth, this is the kind of sort of spectral luminosity that you see from our planet. And recently what I've been doing is just thinking about, well, if you were really a Kardashev Type 1 civilization, which might take us, a while to get there, it may be 1,000 years, it may be 10,000 years, but if you were a Kardashev Type 1 civilization, and you just scale the leakage sort of linearly, depending on, the power that you use, then the spectral luminosity leakage of a Kardashev Type 1 civilization would be something of order 10 to the 5 watts per hertz. So if that's true, then you can actually sort of work out whether that's a kind of number that's actually detectable by the current technology, the current sort of telescopes, radio telescopes that we have at our disposal at the moment. I don't want you to worry about what a Jansky is, because it's one of these weird radio astronomy units. It's got a long history and very interesting, but just think of this as being an extremely faint source. Whenever you see micro in front of this, then this is a really faint source. It turns out that, this Kardashev Type 1 civilization, if it does have a spectral luminosity around this value, then that's the kind of flux density levels that our radio telescopes can detect today. And pretty routinely. Now, you have to say that this Type 1 civilization is only 30 light years away. So it's really on our own doorstep. And there are really not many stars between here and 30 light years. So if we're just able to detect this kind of source, then we're not going to be able to sample a very large volume of the universe with this kind of sensitivity. We need to go deeper if we want to be able to go sort of deep into the galaxy with the potential to detect Type 1 civilizations. So this is another area where sort of going from narrowband to broadband that we can actually gain a little bit, because what you notice when you do narrowband SETI, you'll notice the integration times used by telescopes. So the amount of time a telescope spends on a particular star is much, much shorter than your typical radio observations. Typically, when you're doing radio astronomy, you'll observe an object for several hours, maybe even days. But when you're doing SETI, it's typically 5 minutes on a star, 5 minutes off on blank sky, 5 minutes on a star, 5 minutes off. So the integration time is sort of typically measured in minutes. And the reason for that is that this slope that we see in narrowband signals, due to the relative velocity of the transmitter and the receiver changing, we have no idea what this slope should be. We don't have any data on the rotation rate of another planet with a transmitter on it. And we can make lots of different guesses about what this Doppler drift will be, but it will always be imperfect. And so if you begin to integrate over not just 5 minutes, but maybe 10 minutes or 50 minutes, then unless you perfectly know the Doppler drift, your signal is going to become incoherent quite quickly. Now, the nice thing about broadband signals is that that isn't true. With a broadband signal that we see here, there are many different Doppler drifts in here. But it doesn't really matter, because there are billions or at least millions of devices that are contributing to this aggregate emission. So it doesn't really matter what the Doppler drift is. It matters here if you want to coherently integrate, but it doesn't matter here. And so that means that when you've got a sort of a radio array, an array of radio telescopes, then although individual measurements made with that array, maybe every 10 seconds, for example, an integration time of 10 seconds, they're totally dominated by thermal noise. Right? You don't see any structure in here at all. But provided the phase down here at the bottom, provided that's coherent, and you're following changes in the phase, instrumental changes in the phase, then you can begin to integrate that signal, not over 5 minutes or even 5 hours or 5 days, but you can go up to 5 weeks integrating this signal, provided the data are coherent, provided the phase is coherent. And eventually you can make, very good detections of very, very faint objects. So this allows us, in the case of looking for these broadband sort of radio technosignatures, to have wide, deep fields of the sky where we integrate for a very long time. And radio astronomy, astronomers in general, and the optical, but other parts of the spectrum, we do this all the time. That's how we detect these very faint objects at the start of the universe, is by having very long integration times. But we can do the same with broadband technosignatures as well, in order to go beyond these 30 light years and actually start to sort of go into the galaxy, so that we are sampling not tens of thousands of stars, but hundreds of thousands of stars. So this plot here, this plot is a bit kind of weird. This is what we call the radio source counts. On the bottom here, you have basically sort of the power, how luminous the radio sources are. So if you go in this direction towards the left-hand side of the screen, you're looking at very faint objects. If you're on the other side, you're looking at really bright objects. And it turns out that in the radio sky, there are a few bright sources in the radio sky, but the dominant population in the radio sky are very faint sources. So when you go to the microjansky level, then the radio sky really kind of lights up all of a sudden. So our BRAT, this is a broadband radio technosignature, I'm calling these BRATs. So it sits somewhere around here at 30 microjanskys on here. And that means that if we look at all the natural objects in the sky, because this BRAT is probably sort of, a fairly rare phenomena, who knows? We need to go and look for them, but it's probably quite a rare phenomena. We have to distinguish this source of intelligence, from something like 10 billion natural sources in the sky, mostly galaxies, it turns out. And if we do this integration trick where we integrate for long periods of time and we get into the microjansky domain, then we have to be able to distinguish these very rare objects, these BRATs, broadband radio technosignatures. We have to be able to sort of distinguish those from a background of about 100 billion other faint radio objects. So that's quite a tough thing to do. And, the sky is full of all these faint sources. Most of them are the galaxies, for example, star-forming galaxies that you see at the bottom here. So this is the dominant kind of contaminant from this search for BRATs, is these star-forming galaxies. Star-forming galaxies are galaxies like our own. They're forming stars. We also have some AGN. That's black holes, for example, that produce lots of radio emission through jets that are propelled from the inner part of the black hole, the accretion disk. And then there are also sort of galactic sources. These are all confounding sources. So when we look up at the sky, there are many of these faint radio sources there, and very likely it's maybe the BRATs that we're looking for these broadband radio technosignatures, they're going to be very rare objects indeed. So that means that we have to be able to try and distinguish them from all these other confounding sources. And the tools of the trade to do this, well, we need radio arrays, so we need interferometer arrays. What you see here is the MeerKAT telescope in South Africa, which is probably the best radio telescope around 1 to 15 gigahertz in the world, on the planet. It's a precursor to the Square Kilometre Array. So we need these radio telescopes that can make very deep but also very wide observations of the sky at relatively good but sort of low resolution. We need to be able to also understand the nature of all these sources across the electromagnetic spectrum. So from the radio into the millimeter, into the submillimeter, into the far infrared, the mid-infrared, the near-infrared, the optical, the ultraviolet, etc. We need to understand the properties of all these faint sources in order to be able to uncover these broadband radio technosignatures. And the other thing that we need is we need these radio arrays, but we need them when they have dimensions that the telescopes are separated not by, a few kilometers, but actually 10,000 kilometers. And we need that because we need to have the resolution to be able to localize these sources and to work out what their motions are. So what are the discriminators? What are the things that make these broadband radio technosignatures different from the natural emission that we see? Well, one which I think is really interesting is that, astronomy, astrophysics, usually produces very kind of broadband, very smooth spectra. And the reason that it does that is because in the radio, most of the emission is coming from relativistic electrons that are moving very quickly along magnetic fields and losing energy. And there are a lot more sort of low energy electrons than there are high energy electrons. And that energy distribution is a power law. And that power law finds itself back into these plots where we plot the sort of luminosity of a radio source against frequency. Radio sources are typically brighter as you go to lower frequencies. So this is the kind of thing that we see really no matter what sort of radio object we look at, we see a very smooth continuum. We don't really expect that from these broadband radio technosignatures. There's no reason why a civilization would have this perfect power law. We don't have that. There are some parts of the electromagnetic spectrum, some parts of the radio spectrum where we're producing very powerful emission, for example, civilian radar and military radar systems around a few gigahertz. And then there are fainter parts of the spectrum. And in fact, we also have parts of the spectrum that we protect. So, for example, this is neutral hydrogen that radio astronomers observe to understand the structure of our own galaxy and other galaxies. We actually say that we're not going to transmit in this part of the spectrum. We try and stop people from doing that so that radio astronomers can have a clear view of the sky. So these brats will have a very kind of engineered spectrum. It's not going to be a spectrum that's sort of based on plasma physics. It's going to be one that's based on engineering and regulation and real usage of the spectrum for the kind of things that societies like our own do. So that's one thing that we can look out for. The other things that we can look out for is that these sources will be incredibly compact. Because we're talking about planetary emission, so something on the scale of our own planet, but at a very large distance, then when we look at these sources on the sky, they're very much point sources. You don't see any structure. You can't measure a size for them. They're really unresolved, even by VLBI, these very large long baseline arrays. So that's one thing that we would expect them to look like. The other thing is because this leakage radiation is probably from an ensemble of many different types of transmitter, we don't expect any sort of polarization, dominant polarization to emerge from that. There'll be many different linear and circular polarizations that are being used so that the aggregate polarization is probably very, very low. And then the other thing that we see when we look at our own planet, for example, and when we simulate the emission, our own planet's rotating. So if you're on another planet around another star and you're looking at the Earth, it's rotating. So sometimes you'll see parts of the Earth that have lots of radio transmitters on it, so it'll look very bright. But then there'll be other times where all you see is the ocean, for example, the Pacific, and then there won't be any radio waves. So there'll be a diurnal modulation to the radio emission coming from these systems. And the other thing is that because they're really, really small, because they're point sources, in fact, they're like only a few micro arc seconds on the sky in size, they're going to scintillate. So like if you look up at the sky tonight and if you can see some stars, you'll notice that they change in their brightness. We would expect to see that also with these broadband radio technosignature sources because they're very, very small, and so they will scintillate. So that diurnal modulation that we see here, superimposed on that will be very rapid modulations of the radio signal for these systems. And then last but not least, with VLBI, we can measure the position of these sources with fantastic accuracy. If they are sort of associated with a star, for example, if the transmitter's on a planet, the planet is moving around a star, in orbit around its star, then we can actually, for these relatively nearby systems, out to maybe 1,000 parsecs, a few thousand light years, we can actually measure that orbital motion with VLBI. We can see the position of this broadband radio signal change over the time scale of maybe like a few years. We would see the orbit of the star depending on how tight the orbit is around the host star. We'd also expect to see that the radio emission was maybe offset from the star, so associated with a planet rather than associated with a star. And we have good positions for many stars now from the ESA Gaia mission. And even if it's not associated with a planet, if it's some sort of free-flying spacecraft, free-flying platform, then again, even with VLBI, even if it's a spacecraft that's as slow as our own spacecraft, like the Pioneer and the Voyager and New Messenger spacecraft, you can measure that motion. If the motion is in the plane of the sky, you could measure those kind of velocities with VLBI. So there's a lot of things that you can do. This is a terrible slide. It's made by AI, by the way, but it's a terrible slide. But I'll just give you one example. So, as I mentioned before, these star-forming galaxies are by far the biggest confounder on the sky. If you go down to microjansky flux levels, nearly all the radio sources you see on the sky are from star-forming galaxies. But you can see that they have very different properties from the brats. So the brats are unresolved, they're point sources. Star-forming galaxies are galaxies, so they have a size of a few arc seconds on the sky. This is a very high brightness temperature. In fact, we can probably only put limits on the brightness temperature. This is a very low brightness temperature. This is this weird kind of non-uniform spectrum. This is this very smooth parallel spectrum. You can't distinguish them from their polarization. This is very low polarization, and probably this does too. And then, my goodness, I can't read this, but this is the variations. So we would expect these brats, because of the scintillation, to be varying very rapidly. Star-forming galaxies are huge things, full of all sorts of stars. They just don't vary because there's just so many sources of the radio emission that they don't vary very much at all. And last but not least, the obvious thing is that these star-forming galaxies are at cosmological distances. So they're stationary on the sky. They don't move, whereas our brats should be moving, and we should be able to detect that motion with VLBI. Okay, so I'm not going to talk about bits and bytes, but I just will talk about the fact that in order to sort of begin to see if we can detect and identify these broadband radio technosignatures, we have to probably get to these microjansky levels. We probably have to go even below that to the sub-microjansky level. So we are definitely going to be talking about looking at 100 billion or maybe even a trillion sources that have a lot of complexity to them in terms of their characteristics across the electromagnetic spectrum and maybe even multi-messenger type data. So AI is going to be something that we need to use. There's no way any human is going to be able to tackle the scale, but also the complexity, and trying to understand, where you see anomalies between what is sort of the average radio source and what is, an anomaly that might be one of these brats. So we need AI to be able to do this. We can have this manifold of normality, if you like, and we're looking for departures from that. Those might be the brats that we're looking for. AI will not only transform how we do the data analysis, but it's going to transform telescopes, how we develop telescopes, how we maintain them, how we operate them, how we schedule them. This is all going to happen in the next few years, so we better be prepared for it. And we should also, one thing, when I was young, we were always told that radio astronomy data had no value, you know? And at some level, it's true. You know, if you look at that plot I showed you, that just, you know, it's just dominated by thermal noise. We usually said radio astronomy is just noise. And then we began to digitize data, and we realized that we could actually, by digitizing data, we could actually have a very wide field view of the sky. And there are lots of things in the sky, I can tell you. And a lot of that information is actually very, very useful. So there's that, but also there's just the fact that we are producing more data than most other sort of domains in the scientific domain. And it's structured data, it's labeled data, it's data that I think is really interesting for AI and the development of AI. If you're using AI, and I think probably you all are, you'll realize the impact it's having on your own science. It's certainly impacting my science. It's impacting my productivity enormously. But you can see the future, and I think the future is, you know, there is a big question about what is the role of astronomers maybe in 5 years' time or 10 years' time. And I don't worry about people like myself, but I do worry about the younger generation and PhD students. What role for them is there when we really have not the kind of systems that we have today, but we begin to move towards AGI and potentially, you know, eventually ASI. And the one saying that I have, and I use it a lot, but I actually believe it, is that we're probably going into the realm where it's our machines sort of looking for their machines. And maybe that's the way we need to do it. You know, maybe the bias that we all have as humans, as human scientists, maybe that's one of the things that's actually stopping us from making this big detection of extraterrestrial intelligence. This is my last slide. This is a quote by Frank Drake that I like very much. So he says, you know, at this very minute, with almost absolute certainty, radio waves sent forth by other intelligent civilizations are falling on the Earth. So he wrote this in a book back in the early 1960s. He was thinking of these narrowband signals. He was not, he says that in a few sentences later. He's talking about narrowband signals. And he might be right about the narrowband signals. We should be doing narrowband SETI just because they're so easy to distinguish from the natural background. But I'm absolutely sure that he's right about these broadband signatures. Civilizations, if they're out there, there will be broadband leakage. And they could be sitting in data archives all over the world, just waiting to be detected. I'm going to leave it there, and I'm going to hand over to Adam, who will give the second part of the talk.
All right, thank you, Mike. Hard act to follow. So my name is Adam Thompson. It is an absolute pleasure to be here. So thank you to Larry for the invitation to the Society. And I don't get a chance to do this very often, but thank you to my wife, Teal, who is the first presentation she's gotten to see from one of these. And just really special. So this one is for her, unless my jokes don't land, and then the next one is for her. So we'll start with, this is really a presentation. This is an engineering presentation, and it's on tooling, and it's on what are the types of hardware and software algorithms that we need to build to find extraterrestrial intelligence and to advance scientific experiments. And you see the title has that first word of towards, which means it isn't actually done yet, and it's just starting. And so before I even dive into the weeds, let's talk about what an agentic observatory is. So agentic AI is probably not unfamiliar to you. The technical definition is it is an AI that calls an API. This means it's an AI that actually creates an action, right? So if you open up your favorite AI model, it's like Claude or open it or ChatGPT or what have you, and you say, what's the best restaurant in Washington, D.C., it could come back. I think there was a new magazine that said it's Albee. So it could say Albee. And the AI agent would book you a reservation, hopefully kick people out of line. Maybe you give it your credit card and it like bribes the restaurant a little bit to get you, to get you that Valentine's Day reservation. So let's think about this in terms of a radio telescope or an actual instrument. And so this is the fundamental point of this talk. But before we talk about radio astronomy, specifically in some of the work that we've done over our 8-year collaboration with our friends at the SETI Institute and the Allen Telescope Array, let's take a step back and talk about general scientific workloads. So instruments, this is the instruments are cool part of the talk. These computational instruments are the background and just driving force of scientific discovery. And it's, within the scientific community, you have X-ray and electron light sources. I know you had a previous Joseph Henry talk with some synchrotron light sources looking at old scrolls and trying to find like what was hidden, behind decaying engravings. We also have particle accelerators, high repetition rate lasers, which are fueling fusion energy. And then we also have all of the aerospace defense, radar systems, communication systems, ground stations for spectrum awareness, what's going on in the world. And then advanced manufacturing. So let's look at scanning electron microscopes. Let's look at industrial CT scans, industrial X-rays to say, let's define defects in materials. Let's look at the next generation hardware platform and say, from a component part, like is this power supply malfunctioning? And all of these things come together with saying that you have streaming real-time physical data, which needs to be acted on and learned upon to help drive forward discoveries, whether that discovery is something commercial, whether it's saying this is a defect, or whether that discovery is a new type of particle in high energy physics. And these are also, of course, driving Nobel Prize winning research. So from neutrino observations on the far left, which got the Nobel Prize in 2015, to LIGO gravitational wave detectors, all the way to AlphaFold in 2025. And I want to dive into AlphaFold a little bit more because I think this is a culmination of where AI is heading. So if you're not familiar, AlphaFold, it was essentially an AI foundational model that was used to essentially help with drug discovery. And if you look at the data set that this foundational model was created on, there is a little Swiss company that makes X-ray and electron detectors called Dectris. And they have these X-ray cameras in all major synchrotron light sources. And so in the 70s, Brookhaven National Laboratory started to record X-ray structures of proteins, and they put them all into the protein data bank. So this is in 1971 when this started. And if you look at this slide, more than 84% of the X-ray structures in the PDB were with these Dectris detectors. And then moreover, a third of AlphaFold's training data came from these real-time measurements. So what this means is if we take a step back, in 1971, we created a database of protein structures with X-rays. And 50 years later, that data set was able to create a new foundational model that's driving drug discovery, right? So this is really powerful because when you look at AI as it stands right now, everything that AI knows about fusion energy, everything that AI knows about the search for extraterrestrial intelligence is based off of human language and human images. There's no foundational model for radio frequency data. There's no foundational model for voltage data. And there was no foundational model for these, X-ray protein synthesis until we have this, protein data bank. So again, we're going to be talking a lot about real-time processing on instruments. This is a talk about speed and productivity, but the undercurrent is that a successful instrument makes more foundational AI discoveries in the future. Now, one of the challenges with our instruments is they're just producing way too much data. It's just as simple as that. Within radio astronomy, you see the Square Kilometre Array, so SKA mid is expected to produce about an exabyte of data per year, which is just it's just mind-boggling how big these numbers are. Next generation VLA is 40 petabytes of data per month. Now, these instruments aren't next to a data center, right? They're in the middle of nowhere, and they have to get this data somewhere to process and say, okay, well, how is this working? And this isn't just targeted on radio astronomy, and this isn't just a radio astronomy challenge, because you have the high luminosity upgrade at the Large Hadron Collider. You have light source, so the advanced photon source at Argonne is upgrading, or has just finished upgrading to more beamlines that are producing even more data. And then even with just aerospace and defense radar, you have S and X band radars that have just experienced a colossal data rate growth. Now you could say why, and these instruments are looking at higher resolution, higher bandwidths, increasingly more things. And so we need a way to change how we are functioning with these instruments and with this data, because we're going to be in a situation where our instruments just don't work. Historically, how these are built is you have an instrument and you have a lot of specialty hardware at the instrument. So things like data converters, things like field programmable gate arrays, FPGAs, which are hardware programmed accelerators to do a very constrained, defined set of tasks. So these are things like filtration, data reduction, time stamping, and whatnot. And I'm going to pick on the Large Hadron Collider for a second. And this is a little bit of a misnomer, but I think it sets up the talk decently well, is that if you look at the ATLAS experiment, and are there any high-energy physicists in the audience? So if you look at the ATLAS experiment, they are looking at 40 megahertz of data. So that's their major goal. And they're slamming particles together. They're trying to define the next Higgs boson and fundamental discoveries of the world. Their L0 trigger, their very first trigger, is programmed on FPGAs. And the very first thing they do, multi-billion-dollar instrument, is they get rid of 39 megahertz of data. So can you imagine going to Congress and saying, hey, I got an idea. I want $2 billion to revolutionize radio astronomy. And the first thing we're going to do is we're going to throw out 98.5% of our data that this collects. It's probably not going to go over very well. And so one of the benefits of what our team does at NVIDIA is we're trying to put compute closer to that 40 megahertz so that you have some type of intelligent model, some type of intelligent AI that is looking at this data stream so you don't have misses. You're not just relying on take an FFT, and if the FFT is above some peak, keep it. If it's below some peak, discard it. And this is kind of the foundation of what we do. And to look at this in a slightly different context and think about an end-to-end pipeline is we have this line right here, which is separating what we would consider to be real-time from urgent computing. Real-time computing is at the instrument, right? So real-time computing is if you can't finish and if you can't keep up with the data stream, you lose data, right? So you're losing your observation of what's going on. Urgent means, okay, it kind of sucks if it doesn't finish in time. I may not finish by the scan, it may not finish by the experiment, but I still have my data, right? And so in traditional, I would say radio astronomy in general is predominantly file-based. And so you have your instrument, which is doing all of your front-end signal processing, but kind of the output of this is a file. And you send that file to some HPC, some cloud computing, and you run your enhanced analytics on this. And there's obviously benefits to this type of workload, but what we are advocating for is let's try to the greatest extent possible, let's try to integrate that radio telescope with on-prem GPU resources to help filter through that data, to do your initial BRAT search, to give you, even if it's your low resolution product, to give some type of insight as to what's going on. And critically, if you have this ability to run compute at your instrument, you also have the ability to make decisions of what your instrument is doing. So you can change frequency, you can change where you're pointing, you can change your resolution and do all of these other things. And notably, you still see that we have this connection with an HPC system. So we call all of this together edge supercomputing. And when you think of edge, I think most people think of something that is like small size, weight, and power, you can carry in your hand. And what we're really talking about here is how do you put like data center type hardware, so really fast networking, really fast compute, close to an instrument so that we can handle these terabit per second and hundreds of gigabits per second data rates that are coming from the instrument. But this is only the edge part. This is only saying I have an instrument that produces a lot of data. I want to like figure out what that data means. We also have a connection between an edge and simulation and an edge and AI training, or AI, this AI factory. So your connection from your edge to simulation, so let's say a digital twin. So we have a synthetic representation of our instrument. This is particularly important in fusion energy because, you don't want like the sun to escape from your tokamak and cause a whole bunch of problems. So it's really a good idea to have real-time measurement data from your experiment going into your simulation of that experiment to say, okay, well, these parameters work. So we would call this an interactive digital twin. You also have a connection from edge to AI factory, which is where you're doing continuous learning. And so in this case, you're saying, I'm getting these real-time physical measurements. I have an AI model that says I should be getting these other measurements. I have a delta, and I need to retrain my model that's running in real time at the instrument. And so this is essentially saying that we are training a model and we can update the model weights back to the edge. And then this AI factory is also generating synthetic data, which you can then use to feed into your digital twin or your simulation for improved performance there. So this is why this is drawn like a circle, right? Because everything impacts everything else. Now we're going to get a little technical, and we're going to talk about how do we intercept and how do we put GPUs at these instruments. And before I talk about this slide, I want to talk about GPUs for a second. I started my career at NVIDIA as a solution architect, and a solution architect is essentially a pre-sales engineer who goes to customers and tries to position the NVIDIA platform, so both software and hardware, to that particular customer's problem set. And when I would do interviews, one of my favorite questions to ask would be, use an analogy, think of an analogy to describe the difference between a GPU and a CPU. And when would someone want to use a GPU versus a CPU? So the answer that I had learned, I'm going to say what I learned, and then I'm going to say what I use. What I learned was the analogy of you've just finished a concert, and you're trying to get all of these people to leave your concert or to leave your sporting event. So you have two options. There's the CPU option and the GPU option. The GPU option is a Greyhound bus, right? It's going to go 60 miles an hour down the highway, but you can fit, say, 150 people in it. Now remember, your goal is to get as many people out of the concert as possible. So that's throughput optimized, right? Like you're trying to get the most people to a certain place in 1 unit of time. Then you have your latency optimized solution, which is your CPU. So this is one after another as fast as possible. So this is your red Ferrari that can only take 2 people, your driver and another person. Which one would you want to take? Now I think this analogy falls apart because I would say, well, I want to take the red Ferrari, duh, right? So the example that I thought of was involving grocery stores, which is essentially everyone's been stuck in that situation if it's before Thanksgiving or before July 4th and you forget your hot dog buns or whatever. So would you rather go to, and I'm gonna just, I was gonna name a grocery store, but I'm not gonna do that because I don't want to get in trouble. But I think everyone knows that one grocery store that's never staffed that well, and there's a huge line, you're just like, oh God. So the point is that the CPU grocery store has one checkout lane open, but that checkout lane person is like the Guinness Book of World Records fastest checkout. So like you get there and you're done. So would you rather go to that grocery store that has a big long line, but you get through that line really quickly? Or would you rather go to the GPU grocery store that has like 5,000 open checkout lanes with normal people? And so again, this is another way to think about throughput versus latency. Now, part of the challenge of tying that back to this slide is that when we want to do real-time sensor processing. The question is, do you care about bandwidth or do you care about latency? Now remember, latency is I have this sensor stream that's giving me as much data, like it's a fire hose of data and I need to consume it. And if I don't handle it in the latency windows, I drop data. But I also have a highly parallel algorithms like big FFTs, big matrix multiplications on the GPU, which are throughput optimized. So if you ask this question to a real-time sensor processing engineer of do you want high bandwidth or low latency, they're going to say, yes, I want both. And so this makes it a little challenging on GPU resources to figure this out. So the place where we can say, let's intersect GPU computing with sensors on these systems is in data acquisition. It's called the DAC. And typical DAC architectures are shown over here. This is, again, highly technical, but kind of the point is that you have a data converter, which is doing an analog to digital, you're just digitizing data. You have an FPGA, which is doing some ultra low latency work. And then you mostly have a CPU that's doing processing. So in this paradigm, you're saying, digitize my data, do a little bit of work on my data, and store it to disk. Now, one thing that is challenging is that if you're going to say, I want to add AI to this architecture, AI would probably come at this FPGA. And these FPGAs are hardware defined. They're great at ultra low latency, but you can't put big models on them. They're challenging to program. You can't just like go in with Python or C++ and start to code away at these. So what we've been advocating for is this AI native DAC architecture. So you see that we still have a data converter, we still have an FPGA, but we've put most of our processing on this GPU. Now what this is doing is it's allowing all of the NVIDIA software you see, everything that supports NVIDIA GPUs, can now interface with raw data that's coming off of your instrument. So there's no write to disks in the middle of this pipeline. You can take a PyTorch, an AI model, and run it on real data. You can take, cuFFT, which is an FFT library, or any of these math libraries, and apply it to raw data. So this is really trying to unite people who make detectors with people who use the detectors. And I think a lot of times in the scientific community, you have pick your favorite sensor provider, and they've made decisions to try to make your life as scientists easier, and then you're kind of sitting in a spot where you're like, I wish you hadn't made that decision because I just want the data. And I want to have the creativity to be able to do interesting things with that data. And so the only way this works is if we have it's called a direct memory access, which means if we can take memory directly from this FPGA to this GPU as quickly as possible. And doing this has been doing this has been very challenging because you need to be a network programmer, you need to be a signal processing engineer, and you need to know CUDA, so NVIDIA, GPU software really well. And that Venn diagram of, those three circles, it's like 50 people in the world. And so the goal of all of this is to try to be as plug and play as possible. So when you plug in your webcam and you just get your video, we want you to be able to plug in your radio telescope. And then the output of this is just a tensor in GPU memory that you can then go and build your own applications with. Another super technical slide is we talked a lot about data acquisition, but how do we essentially build an end-to-end autonomous experiment? And this is really trying to delineate the difference between edge computing, which is at the instrument, versus HPC, so urgent computing, which is off-site. And so in here, we have our sensor. It goes through networking with a switch. We have our DAC, which has this GPU and a network card tightly coupled. And then we can move over to HPC, which is doing, similar to what I showed on that three diagram or that three image circular workflow. But this is fundamentally where you can have some agentic AI and orchestration. Because if you have data feeding into each of these components, you have concept of what is going on at each part of your pipeline, and you have different latency and compute requirements, but you see these three feedback loops. So here's a control feedback loop to say, I need to change what I'm looking at. From the DAC, you have, I want to change where my sensor is looking. And then from HPC, you say, I want to change how my experiment is being run in general. So let's talk a little bit about tooling. It's not an Adam Thompson presentation if I don't talk about my first child, which is cuSignal. I have 2 actual children. This is the first. So what cuSignal was, is it was this realization from my own experiences. I'm an electrical engineer by trade, and I finished up my master's degree from Georgia Tech, and I was like, oh my God, I'm an accidental mathematician. And you go to your first job, and they kind of give you this like embedded, this like essentially like an FPGA or GPU, and they're like, okay, like take all the math and like program this. Like we want to find aliens, and you're like, well, I don't know how to program. I'm a mathematician, and so one of the things is that the signal processing community, and particularly the radio astronomy community, were one of the first adopters of using graphics cards for advanced computing. So just accelerated computing. So doing beamforming, channelization, FFTs, matrix multiplication. Actually, one of the first commonly used correlators, XGPU, was developed by a researcher who's now at NVIDIA, and it just permeated through the radio astronomy community because it was taking one of the most painful compute experiences and accelerating it greatly on GPU. And so what cuSignal was about was trying to say, let's take these building blocks of signal processing and let's GPU accelerate them and expose them to a Python API. So it's easy to program, but you can also connect to AI frameworks. So I can do my FFT and I can send it to PyTorch, and we can train a model on these FFTs that were created. And oh my God, I'm showing code at a at a talk. So what this looks like, this is a polyphase resampler. You don't have to know what a polyphase resampler is. And in the code here, this is all on CPU. So essentially what we're doing in here is we're importing libraries, we're creating a big signal, and then right here we're timing our function call right here. So that's with the time it. And so on my computer, which is admittedly a little old at this point, this took about 2.4 seconds. And I'm going to show you cuSignal. So everything you see in green is what's changed. All right, so let me go back. Go back. So here is just regular SciPy signal. This is cuSignal. So this is coding that anyone can do. This is even before Claude code and all these other things. This is a trivial change of just a Control F library replacement. And this is 500 times faster. All right, so the benefit of this type of tooling was, even if you're not going to production with this was the how do you convince your boss that GPUs are a good idea for these types of workloads, is that within a couple half a day of just noodling around, you can get a 500x speed up, and you can say, we can optimize this and go even faster. Another bit of tooling is the manifestation of a lot of this work of doing AI sensor processing, of bringing in these compute libraries like what you saw with cuSignal, is run on an NVIDIA SDK called Holoscan, which is a software development kit to do real-time AI sensor processing. And what it's really trying to do is to build a graph-based API. So you see this is, see right here is that you're basically taking units of compute. So these are called operators. You're connecting them together. And these operators are really optimized to accelerate commonly used parts of a real-time sensor processing pipeline. So how do you get data to GPU? How do you take a trained AI model and apply it to the data that's coming to your GPU? How do you visualize it? And so this is all free and open source code. Most of NVIDIA software is free and open source, and it's available on GitHub. And you'll see in later slides how the SETI-Institute and NVIDIA collaborated specifically with Holoscan to advance the search for extraterrestrial intelligence. So let's go into astronomy. So this will be, the tooling is done. Well, I guess there's a little bit more tooling. But the tooling is mostly done, and we're going to talk about the work that we did with the Allen Telescope Array. But before we do this is a slide that's celebrating, years of collaboration between NVIDIA and the SETI-Institute and the Breakthrough Initiative, a Breakthrough Listen research organization. So in 2019, we released cuSignal, and I gave a talk. I took this slide from SciPy, so that's why you see these SciPy pictures at the bottom. So I released cuSignal in 2019, and I was connected on Twitter, of all places, with the SETI-Institute, now SETI-Institute researcher and back-end engineer named Luigi Cruz. So he had taken some of the work that we did with QSignal, and he had essentially created a framework called CyberEther to run these real-time sensor processing pipelines. And he had this really nice GUI, and you're going to see CyberEther again in the slides as we advance towards an agentic observatory. And then we, in 2022, Luigi had a talk at SciPy about how he used GPUs to advance signal processing, both at the SETI Institute and for his tooling with CyberEther. And then in 2023, NVIDIA released Holoscan. QSignal transitioned to QPi, thanks to a Chan Zuckerberg essential open source for science grant. And then in 2025, this is a little bit of a precursor to what you're going to see, is that we deployed this GPU digital backend at the Allen Telescope Array. So success didn't occur overnight. This success was over, in this case, 6 years of work driving towards a common goal. So the Allen Telescope Array, actual video, we've talked about it a lot. What the hell does it look like? So here it is. It's a 42-element dish. These are all Gregorian dishes. They go up to 3 gigahertz each. And this green, I don't know if I can do it for you on a video. Oh, I can, cool. This green building right here is your data center. So you essentially have all of this data coming from these dishes that go over fiber to this green building, and that's where all of the signal processing magic happens. So what are we trying to do? We're trying to use AI to improve signal search and discovery. And linking back to Mike's talk, this is typically the narrowband search. We're not doing the search for brats at this point. And one of the important things, particularly for NVIDIA, and this is probably for everywhere, is you got to be able to succinctly describe what the hell you're doing and why AI matters. And so I like to use this slide because this is one that NVIDIA Creative made for us. And there was this whole long process of iterations on cartoons of what are you trying to do? And I started with a haystack, and you're trying to find a needle in a haystack, but conventional techniques are only good for straight needles. And if you see one that's bent, it might be that's not a needle. And if you find someone's lost watch in a haystack, it doesn't pick up on it. And so they took my analogy, trashed it, and put it back to astronomy. And so what you see here is without AI, it's the exact same talk track that I used with needles in a haystack, but again with really cool pictures of our friends' little aliens and asteroids and stars and stuff. And so the big takeaway here is that with AI, we're able to find signals of interest that we think we know what they look like, plus variations of those signals that we think we know what they look like, and then also anomalies. So what are the things that are different that we didn't even know to look for before? And there's been a rich history. And again, this goes back to some of the work that we did that even predated the work on the tooling with Luigi. And I want to focus in 2018, this is actually how I met one of Mike's colleagues, Andrew Simeon, is with this work of using a simple convolutional neural network. I don't even know if this was AlexNet, to be honest. It was a super simple deep learning technique to look at spectrograms of data recorded at the Green Bank Observatory to look for fast radio bursts. Now, if you're not familiar with fast radio burst, it's a super short duration, very high energy event. They think they come from decaying stars. And one of the mind-boggling stats is that they produce more energy on the order of milliseconds than our sun produces on the order of days. Right? So it's almost like a mind-boggling amount of energy. And so the big takeaway of this work from Jerry Zhang and team was that they found 72 new fast radio bursts on recorded data by using AI. So this is a direct failure of classical techniques and a direct success of what AI has done. And this ties back into Mike's last statement, that we could have found ET, and they're just sitting on a hard drive somewhere, and we just haven't thought of the tooling to be able to discover it. And then let's move to today. This is an intermediate paper, but let's move to today. So we just published last year in the Journal of Astronomy and Astrophysics a deployed real-time end-to-end deep learning algorithm for fast radio burst detection, which you'll learn more about right now. And what this was doing was we were essentially treating spectrograms as images. So this wasn't, again, we mentioned at the beginning that we don't have some sort of foundational model for RF data. that we're doing right now. And there's been some research, particularly within MRIs and medical devices, of learning from IQ data, so complex valued voltage data that's coming from these radio frequency front ends. And essentially what we did here was we trained a specialized ResNet model, optimized it with NVIDIA software called TensorRT. So this is creating an AI model and then making it fast. And this was trained with real observations and then synthetic data that was generated by a Python library called inject FRB. So there were about 200,000 samples of data that were trained on this. And we essentially took this AI algorithm, we tied it to, I'm gonna skip my slides a little bit. We took this AI algorithm, which was this AI inferencing operator, we put it into Holoscan. We used Holoscan to get data into the GPU from the array. So this was 26 antennas, 96 megahertz, 2 polarizations. So it was 100 gigabits per second going to a single GPU. And we took the array, we pointed it at the Crab Nebula, and we detected in real time with AI the pulsar in the Crab Nebula. Now, we knew this was there. This isn't a new discovery. But this was the first time that we know of, and this is what the paper was about, of using AI as a detector, not a filter. So previous techniques, and you see this 600x speed up here, you see this 160x faster than real time. This was done in relation to the previous pipeline at the Allen Telescope Array called Spandex. And in Spandex, you had an integration time, and you had a matched filter. And the output of this integration time and matched filter went to a neural network. And so this is gone here. This is straight radio frequency data, gets beamformed, it gets downsampled, goes to an AI model, and you find this pulsar. Now this is de-dispersed, so you see it stacked up. If you didn't do the de-dispersion, you would see the diagonal line in spectrogram that Mike was talking about before. And again, this is like a little bit more detail on the tooling here. But the big takeaway is that we are able to, in real time, discover signals of interest within the cosmos, for lack of a better term. Now, this is a visualization that Luigi Cruz created. And this was really this was with an Astron all-sky a press release of trying to show, like, what does this mean? Like, how do you visualize what this AI is doing? And this is just showing, NVIDIA has this classic, we call it a flowers demo, which is basically showing AI detection of what flowers are. So it'll say, like, dandelion or tulip, or, as you see these images scroll on the screen. And so this is all synthetic data. This isn't at rate. And this is really just meant to be in here to ground your mindset with what the instrument is doing underneath the hood. So every time you see a green box light up, that would be the AI model saying, yes, this is a signal of interest. This is a narrow band pulse that drifts with respect to time and frequency, and this is a signal of interest. Right? So hopefully this gives you a little bit better of a mental framework of what this is doing. And the real demo is we took kind of a SETI, we were trying to show, like, how does the SETI Institute work? And so we went to the Supercomputing conference in Atlanta in 2024 and actually had a demonstration on the show floor. And so what you see here in this video is essentially the output of the back-end hardware at the Allen Telescope Array running here. And so this is on repeat. At the bottom, you're going to see a big silver box. I wish I had a better way to pause this. This big silver box right here. Oops, that didn't work. That silver box is the front-end RFSoC. And that data is doing the digitization from an antenna, and then we stream to, I'll just skip this, we stream to a GPU box and then run that AI inferencing in real time. So again, this was trying to show what this actually means for these types of instruments and what do you actually get when you combine compute with the sensors. And the big takeaway of all of this is that the work that we've done with the SETI Institute, and this is kind of the dream of NVIDIA, is we say we're a platform company. So this means that we make tools that other people build on top of that they can then use for their own science. And so this it's being, the work that we did with the SETI Institute is called Stellene now, and it's being positioned as a GPU digital backend for other radio observatories, so including Astron Westerbork for an all-sky survey, and then 2 Square Kilometre Array pathfinders for fast radio burst detection. So the French one, which is Nenufar, and the Indian GMRT as well. So since the title said Agentic Observatory and TORDS, I need to give at least a little bit of update on Agentic Observatory. And so the TORDS part is to say we have to bring compute close to the instrument so that we can actually do things in real time, so we can actually have that API, that AI call an API to affect change at your instrument. And part of the emerging workload that we see, particularly as we add AI agents, is this concept of a little model and a big model that are running in tandem at the edge. And so this little model is similar to that inner control loop that you saw on the edge supercomputing architecture, where if you're not running inferencing in a set amount of time, you're losing data. And this big model is saying, I can relax some of my timing constraints, and I can get some more visibility into how my overall data collection is going to try to make decisions. And so some of this work here is being looped up under a project called Nexus, and there is a remote signal processing and SETI search pipeline, so there's tooling to be able to control the instrument remotely, and this can also, in the future, will feed into other radio telescopes as well, so that you can launch, workloads at multiple observatories. Final slide is essentially some tooling, and you see on the right, I'm not supposed to look that way, you see on the right, essentially videos of the observatory, and then on the left are control loops, which can say, we want to launch this particular workload on the instrument, and then you see, I'm going to hesitate to use this little thing. You see this little orange box right here is possible radio frequency interface detected, right? So there's already some loop-ins to being able to schedule remote observations and then to tag, hey, right here, there's a little bit of an issue. And then when you issue a command, you can then look at, say, the video feeds and say, okay, I can actually see this instrument physically moving, and maybe I've detected that it's like raining, or there's, weather events at the time as well, if we look at more of the imaging pipelines. So I wanted to give, that's my final slide. I hope that gave a good overview of the tooling and kind of the goals that we've been doing, and, the rich history that we've had with the SETI Institute. So really appreciate your time and attention.
Yes, we do have time for questions and some answers. Are we ready, gentlemen?
Yep.
Okay. So our first question will go to the red microphone.
Hello, I'm Savannah Crawford. I'm a longtime member for such a young person. And I am a mathematician and educator. So I would like you to speak more, this is for Mike, more about AI and how it is impacting the training of people who are coming into your position, and then what work is left for them. You mentioned it briefly towards the end of your talk, and I was just hoping you could expand on those thoughts.
Okay, so I see students, especially sort of postgraduate students, using AI a lot, and I'm sure many of you see that. And they're using ChatGPT or maybe some of the others. I kind of worry about that because I know that what those large language models sort of deliver is not always perfect. And so my worry for the younger generation is, how do you build up that experience of knowing, what is real and what is sort of really actually has some errors sort of built into it. So I see that all the time. I see people also using sort of large language models for stuff that they don't really need to be using it for. And so actually, rather than being productive, they're actually being less efficient, because they spend too much on details that are not really important. Like words being perfect. They don't have to be perfect, right? So So it worries me when we have people that don't really have much experience using these tools. Now, I could be biased, but I think someone who's like myself, who's like had years and years of looking at data, for example, and doing things without these tools, and I think sort of trying to understand data at a fairly deep level. Well, you know, this AI tool for me is just fantastic, I have to say. For me, I think it doubles my productivity in terms of the number of papers that I can write in a year, especially single author papers. Yeah, I mean, they might not be good papers, I don't know, but they're no worse than the papers I wrote before. In fact, I would say they're better. All I need is an idea. I have an idea. So the other day, when I was doing this BRAT stuff, I had the idea that one of the things we haven't thought about in SETI is that if you have leakage coming from a planet, then you have an ionosphere, for example, and the ionosphere reflects some of the leakage. So if you're looking out and looking at a planet that has a lot of radio waves, you know, being produced by a civilization on the surface, then you should see this ionospheric cutoff. It's actually a technosignature, this ionospheric cutoff. No one has ever thought of this before. So I put it into Claude, and I had the basis of a really good paper, just from maybe 5 minutes of it churning away. So that to me, this is sensational. Not only that, but writing code for all sorts of complicated matters can now be done in like tens of seconds, even if it's incredibly complicated. So I'm absolutely flabbergasted by the opportunity. I'm a bit worried about the training aspect of it all. I don't think we understand what the impact will be in that, you know. But for someone at my end of the process, you know, someone who's sort of towards retirement, it's the most wonderful thing that's ever happened in my lifetime, to be honest, in terms of scientific opportunity and being able to do stuff that I'd never be able to do in a normal single sort of lifetime. But I do worry about the training aspect, and I should probably stop there. But I'm enthusiastic overall. I think it's an amazing time to be alive that this is happening.
Well, we're going to take a question from Ron Eckers in Australia, who is logged in. As many of you know, he's formerly a speaker in the debate over Pluto's status.
Ron Akers asks, in your introduction, you talked about detecting Doppler drift, but could any civilization smart enough to get a radio signal to Earth know of and correct for the Doppler drift?
Yeah, could, of course, and I think it's quite an old idea that, you know, especially a Type 1 civilization, for example. Well, what can a Type 1 civilization do? Well, it can probably do stuff that we would consider to be magic, right? They're maybe 10,000 years ahead of us. Their technologies, their understanding, their science can be completely different from, you know, what we have here on this planet at the moment. So yes, of course they could know what the Doppler drift was. They could even change the Doppler drift so that it became periodic in some way. These are the kind of things that we have to be open for. These are the kind of things that we have to make sure that AI can be open for as well. And I know a lot of people worry that somehow AI, will put things into sort of different categories and boxes. I think that's more like what AI was when it was machine learning. I think like AI, as it is today, has the flexibility to be able to see all those kind of subtle anomalies that humans will either not think are important or just totally not see at all. So I think, yes, we should never underestimate the transmitter, but we do have this new tool that I think can actually help us a lot in seeing things that we might not expect to see.
And on the other side of that, it's not the civilizations far away, but the method itself. Doesn't it make it more difficult to notice, let's say, hidden assumptions that are baked into, say, the training set or the search?
Sorry, the last part was...
Sorry. Does the use of AI make it more difficult to recognize hidden assumptions that are built into the search? And I think the training sets that we use for these models.
I think he's asking about bias in the training set to begin
Oh,
with.
I don't worry about the biases that are in there because that is the natural order of what it is that we measure. So I don't worry too much about that, especially as we move forward into sort of, real AI systems rather than the kind of systems that, for example, Adam showed in the first paper that he showed there, looking for FRBs and also looking for SETI for narrowband signals. I think what we think of AI as AI today and what AI will be in the future, it'll be much more flexible and much more capable of being able to detect things that are subtly different from sort of like the average standard natural background noisy radio data.
Let's go to the blue microphone.
Hi, my name is Frederica Darima, and I'm a member. Thank you for your presentations. You covered a lot of aspects. However, my question is a little bit expanding on the previous one. How, from the point of view of the generation of data, I mean, this must be, number one, it's not only the spinning. Presumably these planets are also going through their own star, so there are this change of signals. Then if there are, even in our own kind of technology, we went from signals that are, we are now in 5G, we were in 1G a few years ago. So over time, these kind of signals that are generated are many. So there must be a cacophony of signals that are received. And also, how are these signals masked by the natural, like, the spinning stars and everything that, also emit radiation, and there is a confluence of such signals. And regarding your Agentic observatory, when you say, the problem with AI, it does not know anything about the underlying system, the physics of the system, the behaviors of the system. So in my view, Agentic is an opportunity to endow AI with this cognizant system modeling and view. I didn't hear you addressing that part. So how do you view this Agentic observatory? Because that will be an opportunity for discriminating across this cacophony of signals that we're, in a sense, trying to find a needle in the haystack.
Yeah, to start on the
unintended.
To start on the Agentic observatory, this is the grand challenge of physical AI in general. So whether it's a self-driving car that understands, a world simulation model of what's going on in the universe, what's going on Earth as you're driving. Well, maybe it's you get contacted by ET and beamed up.
Maybe
your car's got to figure that out. And so it's a grand challenge, and people are working on it, right? So you see more like physics-aware models. There's Fourier operators, and so it's an active area of research. And so when I say that there's a difference between AI doesn't necessarily understand the physics versus there isn't a foundational model for this particular data set. So when I say there's no foundational model for RF, one could still argue that via LLMs and literature searches, and then just looking at corpuses of data represented as pictures, it can learn the physics, right? And we've seen this with image generation of knowing orientations in general. And there's this classic Will Smith eating spaghetti generative image that had it all wrong a couple of years ago and has it right today. So it's a little bit of a cop-out statement of saying it's an active area of research and one of the foundational things of physical AI. But I think the big part of my talk is that we need to have more people exposed to raw data as it's digitized and start thinking about what AI models trained on that data, rather than opinionated data from, what people think we should be like. Should we be looking at spectrograms? maybe not.
Hi, I'm John Chernyavsky. I'm a member. I'd like to ask about kind of other applications of these kind of edge aware computers. In particular, for the example for discovering new civilizations that are intelligent. There you're just trying to find something, but you can also act on that. So you can actually use these as kind of application systems where you get feedback, and then based on that feedback and also your current data and your data feedback, how do you actually respond to those systems? So I'm thinking of, for example, systems in which you determine whether tornadoes are going to hit your house.
Yeah.
Okay, that sort of stuff. Or the example you guys brought up, which is self-driving cars, because you have to continually monitor the data coming in and integrate that into an action that the vehicle takes.
So I have an example of this that I cut from the slides because it wasn't explicitly on topic. But we have worked at NVIDIA with Brookhaven National Labs National Synchrotron Light Source 2. So this again ties back to another Joseph Henry lecture. And if you're talking about doing nanoimaging on a material, so let's say it's a battery, to try to say, like, how does this battery react under time and pressure, and can we, build better batteries in the future, or other such materials. If you think about the science process, this is a national asset, so a researcher needs to get funding and get time on instrument, and this can take a while. So then they get to the instrument, and they have their sample, they give it to a beamline scientist, they load it into the X-ray light source, that thing scans, it takes 8 seconds to scan, it takes 2 minutes to reconstruct that data, so you finish the scan, you send all that data to a reconstruction server, you get your nano image out, and you kind of go home. So this is for a short scan. Now, there are scans that take hours. And it would be a real bummer if you got your funding, you went to NSLS2, you did your 8-hour scan, you got home, and you realized you didn't have beam on your sample, right? And so one of the pieces of work that we did with HoloScan, with NSLS2, was doing real-time nanoimaging reconstruction as your scan was going on. So it was taking X-ray diffraction patterns from your X-ray camera, doing tychography, so it was doing Fourier analysis to get a scan, and this was giving real-time feedback of how your scan was going. So it was almost like old internet, like the picture kind of does a line scan to update, but it gave you indication of, is my experiment going well? And then setting the stage of agentic experiments, you could imagine having, say, a defect detection AI algorithm that says, you know what, there's something weird in this part of my image, and then you send a command trigger to that instrument to zoom. And so then you come home with a clean data set. So our tagline for some of our work is that if you're a beamline scientist, you go in and you have questions, and you leave with probably more questions. And when with real-time reconstruction, you go with questions, and ideally you leave with answers, and it allows you to be creative as you're doing your experiment.
Blue microphone.
Ciprian Ivanov, member. There are plenty of uses of AI, and one of them is creating better and more advanced epicycles than a human mind can contemplate. But what happens when model collapse becomes an issue?
Do you know this one?
No. Could you maybe say what?
Go ahead. You can clarify your question.
Model collapse being that when AI-generated data is fed into the model as training data, it tends to degenerate all into gibberish.
So I would say in general, my specific expertise and my team's expertise tends to be like a plumber of the AI world. So what we're doing is we're taking the assumption that you have, world-class models that have been trained. And we are connecting those world-class models to world-class instruments and trying to get real-time feedback on that. So unfortunately, I don't have the experience to talk about what happens when AI goes wrong or even how do I best train an AI model on these types of data sets. But I mean, these are obviously very important questions that have to be considered as we drive towards agentic workloads.
So I think that kind of goes back to my point about undervaluing data sources. That, for example, astronomy, which has never been considered to be really a valuable data source, that actually it is a very valuable data source because there's always something different in the data. The data is always changing. The sky is always changing. So your models are always growing and developing because of that. And so I think that brings value because you don't get the degeneracy that you're talking about in terms of models that are being fed by AI so that they degenerate. I think if you have sources of data that are always new and unique and independent from one day to the next, that can make sure that you keep a model as being a sort of healthy, functional model. And I think sources like astronomical data, and I don't just mean radio astronomy, but look at the Vera Rubin Observatory, for example, and all the transients that are coming out of that. I think there's a lot of data when you look at the universe, and I think that can keep the health of models, especially models that need to in the future be grounded in physics. I think that's one of the big steps that we need to make. That I think we can maintain the health of models so that they don't sort of collapse and they don't become degenerate and sort of self kind of fulfilling.
Red microphone.
Hi, I'm Will Deacon, a member. Two great talks. Adam, I had a question for you on the hardware side of things. So you have your signal coming out, going into your FPGA, and then you're feeding that into your GPU. Do you see any changes in that kind of structure? So you're handing off more tasks from the GPU to another FPGA that has more dedicated processors in it, or do you think the GPU will always just handle everything?
I think it's that's a great question. I think it comes down to the most realistic and probably best systems are heterogeneous compute. And so you have, in specifically on that overly technical data acquisition slide I had, is that we did have the FPGA in the mix. And part of that, and this is one of the reasons why I asked if there were any high energy physicists in the room, is part of that is that you sometimes need nanosecond latency decision making, and that's not a GPU, which is not. So GPUs are milliseconds. And so essentially what you're saying is if the timing requirement becomes too stringent for something like a GPU, you have that on another piece of hardware. And there are future potentials for heterogeneous integration, particularly for low latency inferencing, like what does the world look like with LPU integration as well, for larger AI models with a lower latency requirement. And so the GPU is still central to the focus because it brings in the developer community, it brings in the AI models, it brings in this. But I think the real production system is going to be heterogeneous.
Yeah, okay. Makes sense.
I know I'm going to disappoint people, but we're only going to take a few more questions because we're running out of time. So let's go to the blue microphone.
Hi, I'm Apaho Terra. I'm not a member. So you were talking about how on a lot of planets there might be broadband signals from communication networks and other technologies. Could you use AI to decrypt those broadband signals?
Well, that would be really difficult because they're really not detected at sufficient signal to noise. And actually what you're detecting is the aggregate of many signals. If you'd much better sensitivity, then in principle you could. But I think at least what I was describing there, these are extremely faint sources of emission, and you can only detect them when you average them. And whenever you start averaging anything, you begin to lose information. You may get a higher signal to noise detection, but when you average anything, you begin to lose information. And that's exactly the kind of information that you would lose, is any kind of information content, for example. So maybe with the next generation telescope, you could do it. And of course, it would be fascinating if you could. But I think we're quite a way off of that at the moment.
It's a quantum telescope.
Yeah.
Red microphone.
I'm Timothy Thomas. I'm a member of the Society. I sort of have two questions. One, for the NVIDIA expert, that's a really good idea. Move the AI foundational model right up close to the sensor and then do all the process. Have you thought about doing that to humans, where you read my sensory input and tell me what I should have noticed, which I miss all the time, and an AI would be terrific. Does that work? I wonder here on the other point of view, on the issue of no broadband spectrums have yet been detected. What happens if an AI looks out to 1,000 parsecs and says it ain't there? Are you going to believe the AI or your own theories?
Well, I'd go for the last one. Yeah, well, so I think I think you have to trust the AI because it's very difficult to do it in any other way. But you might take a subset of the data and try and look at the way it has gone about its business and to make sure that it's been sensible in the things that it's done. But I don't think you can possibly do that for all the radio sources that we can detect at microjansky source levels. You believe the AI?
We're doing the red microphone here.
I would. You believe the AI, so what does that mean? That you are wrong about the existence of broadband spectrums in the universe?
Well, if they're not there, we're living in a very kind of lonely universe in which we're the only technical civilization, and it's possible. It's possible at this point in time we're the only technical civilization in our own galaxy. I'd be surprised if it's the only technical civilization in the rest of the universe, but you know, it's quite possible. Intelligence that produces sort of a technical society is rare. The only way we can find out is by looking for it. And I think it's one of the big questions that many people are interested in, not just astronomers, but just the general public, and we should be spending more effort.
Hard to prove a negative. Last question will be the blue microphone somewhere. Blue microphone. Stand up, tell us your name.
Okay.
Blue microphone.
Sorry.
And if you're a member, and ask a question.
Elias Kazarian. I'm not a member, I'm sorry.
That's okay.
And I'm economist. Thank you so much for your presentation.
Speak into the microphone.
Thank you so much for your presentation. You make it easy to understand in a way for non-scientists. CPU versus GPU. At some point, I'm an economist, and at some point, you could see the demand for GPU increase in 2023, 24, and continue. While the demand for CPU did not increase so much, and you could see it reflected on the shares of AMD.
Speak into the microphone.
To the AMD, the shares was stagnant. And recently, the demand for CPU increased enormously. So what is the issue? Is that the scientists revisit their view about the CPU, or they found a new area to use the CPU?
So in general, you saw the agentic workflows are driving CPU resources because you're getting back to a do this, then this, then this, then this. And so that's, you know, in a nutshell, my short answer is that it's the emergence of agentic AI versus like large-scale data center training, which was more traditionally from the big GPU growth.
Use the microphone, please.
Is the segmentation of the process who requires CPU more than GPU, or I don't get it yet, you see. Why the CPU came back? Because you segmented the research, you segmented the processing of the data?
It has to deal more with the application more than a specific segmentation, right? So if you're doing AI training, you typically need, particularly for like these incredibly large language models, is you need, you know, hundreds of thousands of GPUs working in tandem to, you know, train these billion parameter models. Agentic AI is an inferencing task. It's not a training task. Inferencing is about like real-time speed of I have this model, I want to run data through it, and I want to get insights. When you have an agentic workload, not only are you doing inferencing, but you're doing a command. And so if you think about a GPU and a CPU, one of the questions that I got early in NVIDIA was, talking about how, it was taking that analogy and saying that, okay, essentially GPUs are making slow workloads faster because you're optimizing for parallelization and throughput. And it was a naive question, but like weirdly insightful. Is someone was like, oh, I got a whole bunch of old server racks, in the back office. Like, can I just put some GPUs in them and they're faster? And the answer is no, because fast GPUs need to be powered by fast CPUs. It's an asynchronous processor. So the CPU tells the GPU what to do. And so like that's how your launching works. So if you take this and apply it to an agentic workload, you're saying that, okay, I have all of these GPUs that have trained this foundational model. I have a CPU that's saying, send data to this GPU for inferencing. I have a result. And then you have a CPU that says, okay, now do this task. And then you have a CPU that says, now do this inferencing. And so that doing that orchestration tends to be more of a CPU-based workflow. Yeah, you're welcome.
Okay, I think that is going to be our last question. But before we close out, I wanted to read something to you from March 10th, 1961. And why would I do that? It's an abstract presented to PSW, March 10th, 1961. Problems in the detection of extraterrestrial intelligent life. And who do you think made this presentation? Frank Drake.
Yeah.
And so there's a long history of PSW entertaining lectures on this particular issue. And with that, let's thank our speakers. And we have for them the usual gifts of a framed copy of the announcement of their talk. One is for Adam, and one is for Mike, or one is for Mike, and one is for Adam. And the ribbons of the society, which we hope you will wear, and a copy of volume 17 of the Bulletin of PSW, which has copies of formative documents and the first president, Joseph Henry's lecture, which has an interesting presentation on how we should conduct ourselves at scientific meetings, and which is still relevant, and three histories of the Philosophical Society. So thank you, gentlemen, very much for entertaining and interesting talk. And before we go, thank you for your patience. We just have a few things to say. Our next lecture will be in 2 weeks. It'll be a Thursday. I want you to note, not a Friday, very unusual. We're going to have a Thursday meeting on June 11th. And the speaker will be Earl Miller of MIT, and he'll be speaking on the neuroscience of executive function and consciousness, which I'm sure will be shortly implemented on an NVIDIA data center. And then on June 26th, our last regular lecture of the year will be Doug Wallace of the University of Pennsylvania. He is a pioneer in the field of studying mitochondria and its effects in disease, and he'll be talking about mitochondrial medicine. And finally, we have the members-only annual business meeting, lots of numbers, on July 17th. Technically in next fiscal year, but we consider it to be the period for this year. And with that, let's thank our volunteers for all the work they've done to put this together. Before you go, be sure to return your name badges. And for those of you who stay for the social hour, when you're done with your drinks, you can put them on that square table over on the wall there. That would be very good. And with that, I will entertain a motion to adjourn the meeting. A second. All members in favor? I now adjourn the 2536th meeting to the social hour.